Okay. Hi, guys. Okay. One thing I wanted to mention, an example of the inverse sign I forgot to mention. Like, of course, if f is a function, then f inverse will be a relation. It may or may not be a function, but it's definitely a relation. So, that is where the most common use of the inverse of a relation will be is when f is a function. Good. We don't know. I mean, you can probably guess, but we don't know which relations are functions. But anyways, so because any function will be a relation. All the usual like inverses and composition. We can all define that. We can define those for relations too. Okay. And the idea is that okay, let R and S be relations. And we wanted to find a relation which kind of combines the R and S. Okay. Find the composition S of R by, well, just the definition you would use if S and R were functions. Okay. Well, X is going to be related to Z if there exists Y such that X is related to Y and Y is related to Z. Or sorry, Y is related to Z but with S. Okay. That's the composition. This kind of seems like a weird way to write it, but if you write them as if you think about them as functions, this is how you would normally write them. So we'll just see that come up later. Another definition. Okay. Let A be a set. Define the membership relation on A to be the set of ordered pairs A and B such that A and B are in A and A is an element of B. Okay. Define the identity on A just to be the set of ordered pairs A with A, where A runs over capital A. Oh, sorry, more people. Okay, and then finally we'll define A times B to be all the ordered pairs A and B, such that A is in A and B is in B. Okay. Okay, and actually, okay, like I've defined a lot of sets, like S composed with R. I've defined this, and I've also defined R inverse. And you know, what's the usual thing for this class is once we define something, we have to show that it exists. And I didn't do that for any of these. R inverse, I also didn't show that was a set. Okay, but luckily, if we can just show that the Cartesian product of two sets is a set, the other ones kind of we get for free by the axiom scheme of comprehension. Okay, construct A cross B, Cartesian product. Okay. Okay. Oh, sorry. Let A and B be sets. And A cross B is a set. Okay. The proof. We would not want to, well, I mean, one option is to define, like, is to say, well, we apply the axiom of Cartesian products. But we already have so many, yeah, like, this is just the issue. We don't want to have, like, whenever we have a definition, we want to avoid just introducing a new axiom unless we really need to. Because then like the axioms used in mathematics would just grow and grow and grow until we couldn't be sure if anything made sense anymore. Like imagine if in differential equations you had the axiom of differential equations, you know, existence or whatever, and then we have, you know, for number theory, we had the axiom of existence of primes, and just on and on. We'd have so many axioms. What would be the point? Okay. So that was a little bit off topic, I guess. Okay, so we want to construct this set from our axioms if we can. If we absolutely can't, well, then we would have an axiom, but let's try and do it without. Okay. So, you know, so we want to find a set such that let's say it's a set X such that A B is in X for all A in A and B in B. And this is just like a puzzle or something. Okay, first, okay, so yeah, should we do that? First, let's construct, we know this is A comma B. This is a set. That's just by a previous proposition. We already showed that the ordered pair of A and B is a set. Okay. How we did that? Well, we constructed the unordered pair of A and B, the singleton of A, and then the unordered pair of those two. And we got this ordered pair. Okay. Okay, so let's think about where these elements live. Notice this is an element of the power set of A. A comma B. This is an element of the power set of A union B. Why is that? Well, that's just because the singleton of A is a subset of A. The unordered pair is a subset of A union B. Okay. And subsets correspond to elements of the power set. Okay, furthermore, the power set of A is contained in the power set of A union B. Because any subset of A is also a subset of A union B. So that tells you that all the elements of the power set of A are also elements of the power set of A union B. So that establishes this. Okay. So now, what can we say about the set with two elements? This is a subset of the power set of A union B. Okay, those subsets correspond to elements of a power set, so that means that is an element of the power set of A union B. Let's just A comma B. Okay, so our set, we'll take our set X to be this. Okay. Okay. Then any ordered pair A and A comma B is an element of this set X. So that means we can construct the Cartesian product. So A cross B is those elements A comma B in power set of the power set of A union B such that A is in A and B is in B. Since if A is in A, B is in B, then the ordered pair is in the power set of the power set of A union B. Okay. Okay, and that's the end of that. So we've shown that the Cartesian product is a set. And then we get those other sets kind of for free. So like, let's do a couple examples. Let R be a binary relation. Let S be a binary relation. Let A and B be sets. Then R inverse is a relation, or I'll say R inverse is a set. 2, S of R is a set. 3, membership relation on A is a set, or the identity on A is a set. Okay, I guess the fifth one, which we've already seen, A cross B is a set. Okay. Oops, sorry, I've been lopsided this whole time. Okay. And just to give us an idea of what happens, so let's do 1 and 3. Of course, this fifth one, that was just what we just proved. But let's try and tick off these 1 and 3 just to see what happens. Again, it's just to use the fact that A cross B is a set if A and B are sets, and then use the axiom schema of comprehension. So let's start with R inverse. So proof. Let R be a binary relation. Okay. Let X be the field of R, meaning X contains all the things which are related by R, basically. And then notice that R inverse is all the elements of X cross X such that X is related to Y. Okay, so basically we construct all the elements which are related by R. So R is a relation in X. And then we take from that basically what we want, the things that define R inverse. Okay. So that therefore R inverse is a set. Which is a set by the axiom schema of comprehension as usual. So that's for part 1. For part 3, we have to show that the membership relation is a set. So let A be a set. Then what is the membership relation? It's those A and B in A cross A such that A is in B, A and B are in A. Of course, if A comma B is in A cross A, that's the same as saying A is in A and B is in A. So we can kind of like cross that off. Okay. So the membership relation on A is a subset of the Cartesian product A cross A. Oh, sorry. Okay, and then this is a set by same axiom schema of comprehension. Okay, the end. Okay, let's do a little example. Let's take 0 to be the empty set. Let's take 1. Let's take 2 to be this. Okay. Okay, so first of all, these are all sets. The empty set is a set. That's one of the first things we prove. Well, in order for it to be a set, we need a set to exist, but once you assume that, you get this set for free, kind of. Okay, so this is a set. Look, this is a set. Then I can use the axiom of pairing on it to construct this set. And now if I have these two sets, I can pair them together to get this set. Okay. And now let's just do, let's join them all up in a set A. Let's try and figure out what is the power set of the power set of A. At least to see that the ordered pairs of elements of A should be in the set. Actually, yeah. It's gonna have too many elements for us to write down, but we'll just try and see what happens. We'll write down some of the elements. Okay, so A just has 3 elements. So now we can write down the power set of A. The power set of A should have 8 elements. So we have the empty set, 3 singletons. Then we have like the kind of complements of all those. Then we have set A itself. That's the power set of A. And what about the power set of the power set of A? Well, that's a lot of stuff. Okay. So I'll actually have 2 to the 8 things. What's that, like 256 elements? That's okay. Have the empty set. Let's see. All right. Because the empty set is an element of the power set of A. So this says, I'll try and put like the justification for being in the power set of the power set of A below. Right? Because the empty set is in the power set of A, well, the singleton containing the empty set is a subset of the power set of A. Well, that means the singleton containing the power set is an element of this, right? Similarly, I can put singletons around everything and I get elements. Put it like that. I can also put any 2 of them together. And then, so I can pair the empty set with anything else. I can also pair and on. And then I compare 1 with anything else and so on. Oops, sorry, I messed up again. Okay, and I can keep on going. Then I can put 3 things together, you know, like and then I can put 4 things all together. And then I can put everything together. Power set of A is also an element. So there's a bunch of different things that go in there. Right, so now let's try and find, like 0, 2. Is it one of these? Oh, sorry. This is the power set of A. Is it one of these? Well, to figure that out, we have to write down what is 0, 2. It's the unordered pair. Okay. And then we will find this, right? Because when I was writing down all the elements of the power set of A, the second step was to write all the unordered pairs of things in the power set of A. And this is an unordered pair of 2 things in the power set of A. So it would have come up on this step. Somewhere in here. Okay. So this ordered pair is an element of the power set of A. There's like 256 things here, so I didn't actually write this down. But that's okay. Okay, we're going to take one last break. Just a 5-minute break. And then we'll go to about, I think, like 4:40, something like that. Okay. So we'll just take a 5-minute break. Use the same link to come back.